Hi everyone, my name is Jaden and I'm here with Ying and Liam, and we are group 86 of the third assignment of the AI Planning for Autonomy subject. Today in this quick video presentation, we will each like to address a point to go into further detail from each of our AI agents. I'll be talking about my value iteration style heuristic that I use. Ying will be talking about her Q-learning approach, and Liam will be walking us through his minimax algorithm that he came up with. First, I'd like to remind you that my algorithm was not actually a value iteration algorithm, but more so a heuristic that was inspired by the Bellman equation update. I wanted to go with an online approach in terms of approaching the game, as Ying did an offline approach, and I thought of a scoring system which was awfully similar to the value iteration. However, it was online. So while I thought this was a good idea at first, this agent performed pretty badly in comparison. And in hindsight, now it makes a lot of sense since value iteration is an offline approach for a reason. In the wiki, I already explained why value iteration is not an ideal fit for this problem, but my heuristic was even worse. And I think this is largely due to the way I applied value updates. Instead of propagating backwards through the state space as in conventional value iteration, my implementation estimates values forward from the current state only, which limits long-term planning and fails to properly capture delayed rewards. And I'll hand it over now to Ying to talk about her Q-learning approach.
This agent used Q-learning to master the sequence game. Instead of storing a massive Q-table for every possible state, it relies on 9 key features to guide decision-making. At each step, the agent picks an action based on the importance of these features and a bit of randomness for exploration. After playing the move, it observes the outcome and updates how valuable each feature is. This way, it gradually learns which features lead to better results. This agent performs better than my previous heuristic function, but it still has limitations. It doesn't plan far ahead and relies heavily on the quality of the features we define. Next, Liam will introduce his Minimax agent.
Thanks, Ying. So this agent here uses the well-known Minimax approach, which is well suited to a 2-player alternating turn game-like sequence. But because of the very high branching factor, we could only use a 2-action deep search. And this also meant we had to use an heuristic evaluation function. Despite this, Minimax still has a good understanding of the opponent's perspective and can anticipate moves they're likely to make. But one key tweak that we made to the algorithm here is to split the action choice process into play and draft halves. And so this means we check which card that places or removes a chip is best separately from which card is best to draft. And the benefit of this is that it allows the agent to assess the impact of drafted cards, which would otherwise be missed at such a shallow search of just 2 actions deep. And then the final action is created by combining these 2 choices. Obviously, we needed to make several strong assumptions to simplify the game to let Minimax work. And this included entirely eliminating non-determinism, as well as reducing the action branching factor. And while these assumptions were necessary, they are potentially quite detrimental to performance. But even with those limitations, we found Minimax to be the most performant agent of our techniques that we tried. So now let's break down a simple game state to explain the Minimax decision-making in a bit more detail. So imagining we're playing as blue on the diagram on the left, and we have a position where we have a sequence of length 3, but the opponent has a sequence of length 4. We're also considering here that we have the cards to either extend our position by playing a chip at B or block the opponent by playing a chip at A. And in this example, we also assume the opponent has the card to place a chip at A on the next turn. So a simple greedy agent would try to extend its own sequence here without considering the opponent's next move. And this would obviously lead to an immediate loss when the opponent plays a chip in position A on the next move, which is not a great outcome. But Minimax here would try all opponent moves followed by its next move and see that any moves that it makes that don't block the opponent would result in a loss. And because of this, the agent would obviously place a chip in A, blocking the opponent, even though this would potentially give up the chance to extend its own sequence by playing in position B, which could increase the heuristic function. But obviously this behavior of blocking the opponent is very important for high-level play because sometimes it's better to reduce the opponent's strength than strengthen your own position. Thank you.